Okay. All right. Good evening, everyone. Welcome to today's talk on generating long sequences with sparse transformers, including MuseNet examples. My name is Mark Donaldson. I'm just finished my last semester at Rice University as an undergrad from the Business Technology Management program. I also have an equivalent minor in Chinese Studies. And yeah, so um, to so I'm really looking forward to doing this paper. I didn't know it was such a big topic because I didn't cover the first one, which is attention is all you need. So I had to cover that one in a few days and then do this one after. So it's a very, very cool topic, and I look forward to sharing that with you tonight. Okay. Before I go on, I want to thank, of course, Michael and Florian as my facilitators. So we're going to cover all these topics here. We're going to just do a quick refresh of what is a basic transformer. I'm sure you've all heard of it already. We're going to do an example of MuseNet, Sparse. We're going to cover the topic, Sparse transformers, and we're going to cover these topics here as well. And some of them are described on the slides, and the rest I'll just discuss with you from the paper. So we're going to review transformers. So basically, what we have is a transduction model relying entirely on self-attention to compute representation of its input and output without using sequentialized RNNs or convolutions, which is really, really unique. It uses few layer feed-forward architecture to perform matrix calculations that are masked matrix calculations. So we're not using any deep convolutional neural networks to do these type of calculations. It's basically matrix calculations. And we also recompute the attention weights during the backward pass to reduce the memory usage, which I failed to include here. So this is the architecture of a standard transformer, and it is a feed forward network with where we use masked multi-headed attention, and then we use softmax at the end to predict the output probabilities or the probability distribution of the predicted outputs to predict what comes next. So here we're using for sparse transformers, we also use a multi-headed attention where we have the scale dot product attention here, where H represents the number of heads, and V, K, and Q. So Q is the query input. K is going to be the key that is going to match the query input, and V is going to be the value at each key based on a probability distribution that is most closely related to the input, which is Q. So next we're going to play an example of MuseNet, which uses a sparse transformer, and we're going to play a MIDI file. And what you will hear is they've used MIDI files as it's a time-coded type of for the musicians here. So MIDI is basically a time-coded value of being able to play different instruments based upon a time code. And what it does is it will play 4 minutes of music based on a sample little input for the MIDI file. So let's do that now. So I like the jazz trio one. That was pretty good. Let's play that. This is all improvised. Okay, so now we're back to the slide. So yeah, so that sample from MuseNet is basically an improvised piece based on a very tiny sample input. And you can see it sounds really darn close to someone improvising on a live jazz band. Oh, yep. Escape, and then present. Okay, Good. All right, so that's one sample. So what it does is it predicts the next token in the sequence to play the MIDI file. So the inputs are tokens, they're stored as tokens, and it will predict the next sequences, and it can do this up to 4 minutes long. So sparse normal transformers versus sparse transformers. So here we have the traditional transformer with self-attention has the following complexity per layer, and then sparse transformer with self-attention has the following complexity. So the difference between the first one and the second one is this one is squared, but the dimensions are the same. But with this one, we take the square root of the input. So we're using only a smaller a smaller size, I guess, of the matrix to do the calculation. So we're using a sparse portion of the matrix to perform a similar calculation. Per attention layer, right? Yeah. Okay.
So what's D?
So D is the dimension, the size of the dimension, which is fixed. The dimension of each, I think it's each layer. D is the dimension of each layer. Yes, that's right. That's right. Yeah.
It should be across the board of your vectors.
Yeah. Of all the vectors. Yes.
Yeah. Yeah. D.
So how do we get a sparse transformer? So basically, so just covering a bit from the beginning, so we use structure residual block and weight initialization, improve training for very deep networks. We create a set of sparse attention kernels which efficiently compute subsets of the attention matrix. And third, we recompute the attention weights during the backward pass to reduce computational memory usage. So here is figure 4. So I've kept the figures and sections the same in case someone's following along on the paper. So basically, this is the block diagram of one residual block of the sparse transformer. Of course, there'll be many more. And the shaded area represents tensors that are checkpointed and stored in GPU memory. So having looked at the code for this paper, you can, I should have included, but you're basically creating tensors that store this area here in memory. So you're only doing it one time and for the output. And then in the single layer, the other tensors, including attention weights and the feed-forward network activations, are recomputed during the calculation of gradients and reducing the memory usage substantially. So it's hard to see here, but you're doing here, here, and all of here.
Sorry, Mark.
Yes.
For the sake of online audience, can you say like bottom, middle, rather than this and that?
Sure.
They can't see.
Oh, they can't see. Okay, so at the bottom here, we have one tensor, and then here at the end here, and in the middle here, and at the top here. So factorized self-attention. So how can we predict what comes next in a sequence with sparse information? So there's several methods we can use. So what we're going to do is we're going to see what a standard transformer will see, and then how we can then learn from that to see how can we create it, use a sparse transformer to produce, or at least produce the same type of output. Okay, so this one I'm going to explain. So this is figure 2. So in section A, so for figure A, we have many layers in network that learn locally connected patterns. So with this one, as you can see here, it will draw, this layer will draw across this way, vertically. This one will draw across horizontally here. And these are layers 19 and 20 within the deep neural network. And then
just maybe explain what it's doing, right? So the highlighted pixels are where the attention is.
It is for the input
so,
vector. Okay.
Yeah, you assumed that.
We assume that. Yeah. Okay.
No. Yeah. Go ahead.
Okay. So just to re-clarify. So wherever it's being drawn here is where the attention is for the input vector, right?
Where the highlight. It's actually
The
the
hi-
highlight.
where the highlight
so
is
the
here?
The next node, it's drawing the next node at each time step, and it's the actual highlight. So there's a band following the next node.
Following the next.
Yeah, and the band is following vertically there with
Oh,
the next node.
Oh, okay. All right. Okay.
Yeah.
All right.
So
Okay.
on the left side is horizontally and always takes the row, right? And takes the attention from it, and it predicts the next pixel.
The next one.
Yeah,
Okay.
and then the right image, it's vertical.
Oh,
And then in the deeper layers, what you want to show in the next slide, they just combine those things.
Oh, okay. Okay. I see what you mean.
And
So this bar is the attention, and then this is what's going to be drawn next.
Yeah.
Yes,
Okay. I see. Okay.
you got it.
So I guess here with the white dots, for example, is where the attention is being
Yes.
drawn from, and then we're predicting what comes next.
But those are much deeper layers now.
Yes, these are layers 64 to 120, 64 and 128. So 64 on the left, and then what layer 128 on the right.
And it was 19 and 20 before, just as a
Yes, that's correct.
Yeah.
19 and 20, and C and D 60 layer 64 128. So you can see here some of these positions activate rarely and sparsely. So different layers will give attention to different features, I guess. So you have like maybe like color or the gradients between features, I suppose, right? And this is all matrix calculation as well.
So just to clarify, the previous sort of slide, is the last one the one that you're sparsely sampling? Like what's so you showed us 4 images, some of them vertically, some of them horizontally, attending over, and the last one you had a sparse sampling. I just want to know what was the point.
Do you want to? Sure. Okay.
Okay, so what Mark said actually at the beginning was this is what an actual transformer that is not a sparse transformer learns. So they kind of actually, you just train up a standard transformer on doing image processing in this case, and then you actually look at where are the actual activations, where are the highest values in the attention matrix.
Yeah, so this is CIFAR10 as an example of the image source.
Yeah.
And what they did was studied how the transformer network, where it gives attention to for the inputs, and then they determined that, well, it doesn't give attention to everything. So therefore, we can create a sparse transformer to produce the same result at a lower computational cost.
So that horizontal or vertical attention bands, did they occur with training? That they're not like any.
It just learned
These are where the network is giving attention to.
Where it learned to give
at different layers. So different layers will give attention to different things. So
it's interesting that it decided to pick up a horizontal or vertical.
Yeah.
lines.
So that's what I think. So isn't it the case that you are deterministically looking at it vertically, and then within the band, then it has variable values. Is that?
Some places are like brighter.
That was my understanding from the paper.
oh, I see what you mean. Like
Yeah, for
here,
example, the
as it goes
second
across,
row
right?
at the top is not actually that bright.
Yeah, so you force it to look at only, that's my understanding, but please correct me if I'm wrong. It seems that you're forcing to look at only the previous vertical or horizontal sort of line, and then within that line you can see variability of the attention.
Yeah.
So you're only visualizing that. In the previous line, whether vertical or horizontal, what did it pay attention to?
So this is still sparse, but it's like they have artificially made it sparse by making it look at only vertical or horizontal lines.
So my understanding at least was that, and I could be wrong, was that this is actually just what is learned. Yeah. But when they actually do a sparse transformer, they then a priori or they like deliberately structurally design the model to actually have that structure later on. But my understanding, like if there's a blog where they basically, and in the description they basically say, if you just take a stock transformer, this is what you end up with. Why would I say that? Well, if you go to the next slide, here you're seeing these really complicated gradients and stuff like that. the sparse transformer never does anything. Like when they actually do a sparse transformer, these types of filters would never exist at any layer because they only do either the horizontal and the column. So that's another indication to me that this is the association matrix or attention matrix that is learned from a stock transform. But I could be wrong still.
So
does that make sense?
So I think you just want, so you don't really need to take everything in a matrix multiplication to predict the next value. So what they're doing is they're sparsely taking things that are more strongly related to the input vector to predict the output. So that way it's computationally less expensive.
Are you talking about this?
This is what we see, and then they say, all right, well, we can do more with less.
So the way I understood it is, if you go to the very low level, and this is what they assume is like this kind of fixed sparsity. So you still have a lot of this fixed sparsity, which you see, and you have like multiple blocks for each sparsity block. And then in the higher level, it combines all these things, and then it can create these kind of complex filters, or this kind of complex attention, even though you only have, at each layer, you only have this kind of sparse. But because you can combine the multiple heads and then the multiple blocks of the sparsity plus the previous layer, and then you can create this kind of complex attention.
Yeah.
And even without looking at all possible n square combinations, you just look at the square root of n for each layer.
Yes. I think if there's one analogy I can give is like, say you're sampling something. Your sampling rate, if you oversample something or undersample something, it's going to sound really great or it's going to sound really terrible because there's a lot of missing information. But what you're trying to find is the optimal point where you have enough information to predict the output. And I think this is what sparse transformer, as an analogy, this is what using sparse transformer is trying to do within the architecture.
That's a question over here.
Yeah. If you call it a factorization, I would imagine the process involves multiplying two, small matrix into a low-rank matrix. In this case, does the two attention heads, the output of those two attention heads being multiplied together?
They're multiplied, and
There's a few different ways they do it. You're gonna.
There's three ways. There's three ways they do it, and I'm going to describe that.
So why are they called factorization?
They're being hand wavy. You can think of it loosely as a form of factorization.
I see.
Yeah.
I think the remaining question on this slide is, why is it the case that you have sort of a sporadic attention on the last image, but pretty neat ones in the previous one? Isn't the case? Or previous ones actually? Is it the case that you're looking at a deeper self-attention layer, and that's why you're getting a bigger receptive field?
Yes. So if you, as you are using the attention of the previous layer, you're also looking at the weights between each one, and each one of those gets fed forward and will reveal different things based on, I guess, the activation from the previous layers, and they all culminate to the end, or the output, which is going to be what's generated next. So at different depths, you're going to have attention given to different things based on the activation, like the weights, and of the previous layer that was attention was given to in order to predict the outcome of the next one.
I think Florian wants to add something.
Sure.
So it's absolutely right what you said.
Yep.
So when I looked at some of the attention papers, and sometimes they visualize the attention layers, you see they say, oh, this layer has kind of like a general attention, like it's kind of like a unbiased look on everything. And then if you go to the deeper attention layers, then you get this kind of more complex patterns. So it all depends like on the key value pairs you keep multiplying with, right?
Yes.
And then sometimes it's not even the first layer, like somewhere in the middle, there's somewhat like a prior equal distribution of attention on all the data points and all the positions.
Mm-hmm. As they move through each one based on the input from the previous that attention was given to times the weight, then you're going to get different different phenomenon that each layer will look at to predict the next one as it's fed forward to the network. Sorry,
To put it in summary, it's like
for each point we have come up with a function that tries to sample efficiently to regenerate this point that we're currently scanning. Is that the idea?
In the original attention
Yeah,
model,
and
yes.
So
Yeah.
okay.
I mean, if you think about it, right? Like in the early days, you would just put fully connected layers everywhere, right? And we don't do that anymore. So in an interesting way, you could sort of think of this as being like, with attention, we were doing the same thing. You're just looking at every possible association, and the cell is you don't need to do that anymore. That's really all you need to take away from this.
Yeah.
Yeah.
Is it showing one head or two heads?
This would be two heads, yeah.
Well, like one
Well,
layer is on
multi-head,
the
yeah.
left side, and then one layer is on the other side.
But
For all the heads.
this is the multiplication of two heads, then you won't see the thin line in the previous picture. You will still see a blob.
I'm not
The
sure that
previous-
they go into that nuanced detail of it. Like this is pulled from, this is actually pulled from the blog. Like the actual GIFs are pulled from the blog, and they're kind of doing it at a more general level. I don't know if they explained it at that level.
And they're very sure that it's two head. The combined output of two heads.
Okay,
Yeah,
we could talk about it.
Yeah, it'll be multi-headed attention. Yeah. Okay. So here is this is the factorized self-attention scheme, and this would be a normal transformer, and you can see this one is sparse but strided, and then the next one is sparse but fixed. So for sparse strided, we typically use these for image patterns and music, things that have some kind of sequence or rhythm to them, so that it's easier to predict the next value, like there's a distributed sequence or pattern that is easier to predict. And then this one here is for fixed, is basically used better for text, and in the last section for the experiments and results, you will see the performance difference between the two.
You might want to like kind of walk through and unpack what this is showing. Yeah.
Okay.
So maybe start with the one on the left, or unless everybody was.
Is that a weight matrix?
So this is a 6x6 input image grid here, and this is what you would see from the vertical and horizontal for the image grid. So like say this is CIFAR 10, this is how you would read that image. Okay, so
The blue is the attention, right?
Yep.
So the dark is the node that I think you're actually looking at,
This
right?
is here.
And then the light blue is
What you're giving attention to.
what you're actually paying attention to. So all of the previous X tokens that you're actually paying attention to in this case, right? So you can see that it's a shorter window, obviously, on
This
the other
one's
side.
here, and then here as well. So as Mike said, you're giving attention to everything before it for every single layer, and it's computationally much more expensive than here, where you're only giving attention to. Here you have going across this way, but you're only giving some attention to going that way, and you can see how it's strided here. So there's a fixed stride between each one, and it's been found that when you do strided, it seems to work better with information that has some kind of recurring chain or pattern or sequence to it, like music, images, things of that nature. It has been tested on other types of input vectors, but it's still in progress. This one, however, works best with text, like the wiki. I think it's called the NWIC vector input as well. So it can go really, really far along into predicting the future output.
So if you look at the middle image, the way you can see it, I have like this kind of row attention and a column attention. In the row attention, you see like, if you look at the diagonal, and you see there's like kind of a continuous relationship between the elements in the diagonal. So the further away you are, you don't have any attention, because right now it just goes for 3, right?
Yeah.
So for the
It goes
top
so
left,
far, and then
for the top left corner, it just influences the next 2, and so on. You influence the next 2 or the previous 2 the way you look at it. And then on top of this, they have the column one, where they say, okay, we have this light blue diagonals, which gives us like another view on the higher level relationships.
Okay.
And this works for images or video, audio. The way I understand is because it's like you said, it's a continuous.
Yeah, it has like melody, rhythm, and the information is a pattern to it.
And for text, they have these kind of chunks, these kind of blocks. Here it's just like 4, but in reality it's much longer. And the idea is like, the sentences are structured, right? Or the sentence, there's like substructure in a sentence, so you don't really need attention too long or too far away.
Yeah. Anything else? Yeah.
How do you get from the top 2 matrices to the bottom one?
How do you get from here to here? That's a good question.
In the bottom, the rows are outputs, the columns are inputs.
It's 36 default.
So it's like kind of expanded.
Yeah. So this times that is expanded into this. Any other questions?
So that's why it's factorized. So these two.
Yes, it's a simple matrix calculation. It's factorized.
So the way you can think of it is you have 6 by 6, right? And all the previous images can influence my current image. So this is essentially all my input data, the bigger metrics. You want to predict the next pixel. And for the attention, in the far left case, you see like the attention each pixel can attend to its other. Like you have all the possible combinations. And then because of this sparse transformation in the middle, you see we kind of cap it, we kind of reduce it. So not every pixel can influence all the other pixels.
So you essentially factorize it, and then you put the attention on the factorized matrices? Is that what it is?
It's not really factorized, but you can think of it as like we're simplifying that big blue thing to this more simplified description. I think the intuition really though is that don't try and perfectly map it, because there's 6 blue squares at the top and there's 3 down there. So clearly it's not a perfect mapping. But the basic idea, you have a solid chunk of blue, right? That's the left top one. So that's the row check. And then you have a column check. But a column check is just you're gonna check 5 back and then 5 back again. So if you look down there in the bigger matrix, at the back end there's a lighter square, and then you'll notice it's 4 back, and then you go 4 back again, and then 4 back again. That gives you effectively a column. Does that make sense to everyone?
Can you point at the squares and describe that?
So go to the very
Right here.
bottom. Go to the very
1, 2, 3, 4, like here. We're here.
very bottom one. Yeah. See, so there's a white square. Now count 4 back.
Okay.
No, that's 4
This
up.
way?
4 back. 1, 2, 3, 4.
Yeah.
White square.
Yeah.
And then I know you can't
1, 2,
see
3,
on the
4, and then
line.
going back. Yeah.
I don't know what to do. If you just look at it and count 4 back.
Yeah. Then it's So 1, 2, 3, 4.
That's a column, right?
Yeah,
Like a column is just an iterative back step.
Yeah.
Or a strided back step. And again, they link it to like strided convolution. They link it to a bunch of stuff in other domains. But the gist is that you're making that big matrix simpler.
Yeah, and it's not convolutional. It's a matrix calculation. That's the other thing too. It
It's
behaves
not
like convolution, but it's not.
So if it's not factorizing, it's loose factorization. So what is it?
It's just a simplification, actually, but you can think of it loosely as effective.
It's sampling, right? Like you're sampling a subset of the values available to you.
So yeah.
You're sampling, and then how you're sure that this sampling shouldn't be context dependent, because for example you have different images like from CFAR, and then one sampling method could be the best option for them if you change the data set. So
That's a great discussion point.
Yes. and it's correct.
Yeah.
Okay. All right.
Just one thing I want to add. So what it does is makes the matrix sparse, right?
Yeah.
And once you do the matrix multiplication for sparse matrices, there are a lot of tricks you can do. Because all the values become 0, right? So you have like a lower triangle matrix, and then now you make 60% of this lower triangle matrix 0, and then do the multiplication of those 2 matrices. You can leverage a lot of optimization.
Sorry, I couldn't get that. What makes us what changes this dense matrix to the sparse one? How we do this transformation from dense to
There's
sparse?
3 ways, and we're going to describe that. There's 3 ways to do it, and we're going to describe that. Yeah. Wow. Sort of. Yeah.
Right.
All right. So this. So in all of the transformers, you'll see variations of this equation, which is basically the theta is going to be the the network or the sequence of tokens that are input into the network. And then we're going to try to maximize the log probability of the distribution of the data. Simplified. So then next, so this is for factorized self-attention, which is what is used in the sparse attention. So, all right, so I'm going to try and explain this one here. So basically, we're giving attention, or we're going to attend. X is going to give attention to all values of S. Okay, and this is going to be in a matrix vector. And then for here, once we have that, then we're using softmax. So why are we using softmax? We're trying to do the probability distribution of all of the weights that were given to each, how can I say? I guess each input that attention was given to times the key or the transposed key value of the input S. And then this is just the square root of the dimension. So this is going to be the sparsity of that matrix, okay? And then, of course, we're going to find, multiply by its value. So the value at each transposed key within the matrix is what we're trying to determine. And the one that has the greatest probability is what will be predicted next to draw that image. Like if it's a horse and it's going top to bottom, it's going to say, okay, this is a leg, we'll draw more leg. If it's a song and a pattern, well, this was the note that came before it. Well, we're going to play this next note, as if you can see it that way. Okay.
Sorry, what is I?
This is the input.
No, it's the.
Isn't it?
It's the type of factorization.
The type of factorization.
Yeah.
Okay.
So if it's a row or a column,
here?
think of it as if it's a row or if it's a column or whatever else. However else.
That's a head. No.
No, am I wrong?
I'm not sure, because for me this right now looks like normal attention. This is this is just the attention right now.
Yeah. So like your denominator over there, that's the normalization you do on attention because of.
Yes. No.
Yes.
It is standard attention. It's just that. So yes, in multi-headed attention, you would have your SI is just a full possible matrix, right? Remember going back to the last one, it was that big triangle matrix. In the factorized, this is why I said you could use it as a bonus slide, but it's fine. In the factorized attention, each head will do a slightly different thing. But again, in the next couple slides, we're going to talk about how there's more than one way you can factorize.
Okay.
Sparsify. Sparsify would be a better word.
So they have two things, right? They have the heads and the blocks, right? Factorization blocks and the heads.
Yep.
So
Yeah,
I are here the heads, or are those the blocks?
It depends on the type of aggregation. So in one of the types, they do it in parallel. So each head would have a different type of factorization, and then they concatenate at the end. So then your heads would be. But in another way, they do it in sequence.
Sequentially, yeah.
Yeah.
And
So it depends on which one you're.
Yeah, and I think we're going to describe that later.
Yeah.
Just quickly, what was the S?
S was the connectivity pattern between each one. Yeah.
I'm not sure if it helps or if it applies here. Usually, I and J, they respectively denote one denote into input, the other denote output. I'm not sure if that's the case. So SI is for each output. You have a set of input that you want to connect to. Is that the case?
Yes.
But then in here, J means J exclusively denotes inputs, and I denotes output.
Yes, and
in some literature, that's
and then this is for the key, and this is for the matching value for the key.
Yeah. I wouldn't don't worry too much about this because in the next slides it makes it clear.
Okay. All right. So I'm going to explain this one. So for this one, it has P separate attention heads, right, which we're trying to describe here, where the nth head defines a subset of the indices, right? So here, the subset of the indices for, let me see here, which is A. And what we're doing is we're looking at the, let me see here.
So A is the type of attention.
Attention per head. Yeah, per n head.
Well, it's an equivalent. So SI equals AI.
Right. Yes, per head. Right?
Per type of factorization.
Type of factorization, okay. And then we're looking at efficient choices for each A.
Right, because we want to know, should we do rows and columns? Should we do a fixed thing? Should we
Or
do weird splattering
Sparsely,
blobs?
like what we saw in the images earlier.
Yeah.
Okay.
But they
And then,
don't use a whole bunch of complex stuff.
yeah, and then we're looking at, for the second one, for every j less than I pair, we said every A such that I can attend through j through path of location with maximum length p plus 1. So we only want to look forward one path for attention, if I understand that correctly, right?
Because you're using a ResNet.
ResNet, yep.
So there's a
And
skip connection, right?
so we don't want to look too far ahead, because then we're not predicting it. We're sort of,
I think.
right?
Am I
Yeah.
saying that right?
I think that's right.
I think so.
Yeah. And so then we have, for each attention head, for here we have A for each attention head here, or for the set of, and so on and so on.
Remember, the underlying idea here is that we're actually going to, in some real way, even though we never actually achieve it necessarily, factorize that full matrix. So really what they're saying is we can approximate the full matrix using this description if we think of each attention as aggregating across, like as Florian was saying. You process through a bunch of different types of filters or attentional filtery things, and at the end you approximate something like a matrix. That's really, I think, what it's trying to say here.
So
It could be way out to
would
lunch.
it be helpful then to go back to the diagram?
I think it would be helpful to plow ahead.
Sure, okay. Okay, sure.
This is actually the meat of it right here. So
Okay.
They actually start telling you how they're actually going to use these so-called factorized transformer heads.
So the first one, okay, so we'll get into this. So the meat of the matter is, the first one is standard dense attention, which simply performs a linear transformation of the attend function from equation 2 earlier. So attention x is equal to the, let's see here, WP is the post attention weight times the attention of the, which was S, which was what, the input? Let me check here.
Attention.
The connectivity pattern, right?
I think 5 is actually the stock transformer, no?
Yes.
Yeah, I think
It
5
is-
is the
is
stock
the stock-
transformer. So it's really 6 that we want
6
to
that we
jump
want.
to. Yeah.
So, and this is R and P is for the,
They're basically, it's a sequential layering.
so
right?
R is the
So-
index of the current block, and P is the number of factorized attention heads.
Yes, so if you have 5 different factorization heads, what you're effectively going to do is you're going to say, okay, use the first head. Now, in the next block, use the second type of head.
And then
Now-
so on and so on.
And that's why by the end of all 5 blocks, let's say if you had 5 different types of factor, like row, column, whatever types, you would get the approximation of the full matrix to the extent that your factorization actually does approach it.
And
In
then
the
there-
examples they were using before, it doesn't perfectly approximate, right?
And then they use, I guess, a concatenation of all of them at the end.
No, that's a different type.
Okay.
So each thing in the A should be much smaller than things in the S. So that's the idea.
Yes.
Dimensions, yes.
Okay, yeah.
Or it's the same size and you just go further back in time.
It's like it's the same dimension, but they're just a different pattern.
Yeah.
So the size is the same. Just what you look at is different.
So you're
Per
actually
attention head.
further back in time in sense.
Could you quickly elaborate the superscripts R modulus P again?
Yeah.
Modulus? I'm not sure.
So R is the index of the current residual block here, and then P is the number of factorized attention heads.
Right, so you're just going to loop. You're going to go factor head 1, factor head 2, factor head 3, then in the next block, factor head 1, factor head 2, factor head 3, then in the next.
And continue on and on.
Until you hit 128 or whatever they want to.
Any other questions on the slide? No? Okay.
It's a very fancy way to write something very simple.
So the second approach is the merged attention head. So here we have a single attention head to the locations of the pixels that both factorized head would attend to. Okay. Sorry.
So you're doing it in one step instead of in 5.
Instead of 5, right? It's all done once. Okay. Can I move forward on this one? Yeah.
So that's a parallel.
No, that's not the parallel. The next one's the parallel.
Okay, so the third and last one is multi-head attention, where the NH, the attention products are computed in parallel. and then concatenated along the feature dimension.
They're just being thorough.
They're just breaking it down.
Yeah.
Okay.
So this is the most familiar that most people should be familiar with. You have more than one type of head, but in this case, the more, and you're also going to get the best parallelization at this case, as Florian was saying. But unlike the standard transformer in your multi-head, each of your steps are not going to be equivalent, right? Or well, they may not be equivalent in a multi-head, so that's not a good. They don't approximate the full association matrix or the transition.
So in a multi-head, each head would look at the same possible combinations, right? At all the same relationships.
Yeah.
But here, each head looks at one type of relationships.
Yeah. And only one. Okay.
And only one. And that's why you can parallelize it. And they just all run in parallel. And then they all each return your value, like a key value pair. It's kind of a similarity score. So they all return you a similarity matrix. And then you concatenate them all. And then you multiply it with the WP matrix.
The WP, and then you do the softmax,
and then you repeat it again. And then you repeat the whole thing again.
From the beginning.
So that's the closest to the original transformer, but again, it's not symmetric anymore.
So you're still using all those. If I'm correctly interpreting the I superscript, you're still using all those different types of factorization, but you're just doing it in parallel.
Yeah.
The way I understood it, and I might be wrong, is you want to predict this pixel, right? And then you look at the different eyes, so you kind of keep shifting the eye back, right? And then each head is like also the column, so you shift multiple columns around. And then you combine all these heads, and that's where you get, in the end, this very complex pattern, where you have like, oh, this pixel is very interesting.
But you don't consider the relationship between them.
So for each head, you just look at one row and then you shift a row. And for each head, you look at column and you shift a column. And then you combine all of this.
Right. I mean, like in the second one, I guess you consider the relationship between the heads. But in this one, you just ignore it. Like they are independent.
So within the head, you just look at what you're looking at.
Right.
Then you concatenate. And the WP kind of allows you to look at the relationship across the heads. And then at the same time, you have multiple layers of this attention, right? So at the same time, you repeat this over and over again, allowing you to capture higher relationships.
Any questions? Okay, so now we're farming away.
We should have expanded those 3 slides into 20.
All right, welcome back. We're going to go over the experiment results. So on the left, we have our table and summary of findings for the density model task. So here we have CIFAR 10, NWIC 8, and ImageNet 6464, and we can see the bits per byte. I'm going to ask Florian to explain for me the bits per byte again, please, if you don't mind.
Prediction, you have the negative log likelihood, right? Yep. Between your predictions and your references, right? It's kind of like the distribution, how similar they are. And then just normalized it by the image size and basically how many bits for the color encoding was used, if it was 8-bit or 16-bit.
Okay, all right, thank you. So here we can see, based on using the strided sparse transformer, we have a very low value of 2.80 bits per byte. For NWIC 8, which is the Wikipedia input, we're using sparse transformer fixed at 0.99. So as I described earlier, when we use strided, it performs better for things like pictures and WAV files, MIDI files, things that have some kind of recurring pattern. And when it comes to text, like NWIC 8, we can see it's going to be fixed, and we can see it performs very, very well for text-based inputs. Let's see. On this side, we have table 2. So sparse pattern shows an increased speed, but also better loss on the data sets, where you compare both.
Excuse me.
Yes?
Can you write it? What does this bits per byte mean? What does it show essentially?
So it's the entropy. So it is, because the lower it is, the better, right? So I catch it now. So basically, let's say you're looking back into some history. You see you have some context, or paying attention to something. Then you're predicting you're predicting the bits of your prediction. If it's language, it could be a character. If it's image, it could be a pixel, right? So how many of those did you what's the perplexity of those? So like how if it's a lower value, that means more of them you're getting correct.
So it's like for having a byte, how many bits I used to like decrease the uncertainty? Is that the idea?
So yes. So how yes. So how exactly? So how uncertain you are in predicting your bytes, right?
So what I have read that in some papers they describe it as a kind of like compression loss. If you use like variational autoencoders or some other autoencoder methods, right? You do the encoding, you do the decoding, and has like a variational or GAN element to it. And then I say you don't want to lose information from those images. And then if you have 0, you make a pair of reconstruction, you have like 0. And then if it's like more errors, is the higher.
So it's like a representative of the information which is lost in the learning process in here, right? So the lower is the less information is lost?
In a sense.
Yeah, in a sense, some people describe it this way. I'm not.
So if it's,
feel free to correct if I'm wrong.
Yeah. So if it's 0, then you're predicting everything correctly.
Your distributions are the same.
Yes.
Your model distribution and the
It's
real
the same as the
distribution are
data.
the same.
If you think of it as like a big giant cross entropy across all the channels of the full output, like all the pixels?
From my understanding, you actually do just start with your cross entropy and then you read, as Florian was saying, you're just renormalizing it. So it's literally cross entropy. It's just they've readjusted. It's no longer log E, it's whatever. They've just readjusted it in order to account for the size of the image or the size of the text, I guess.
Is there a standard starting point? So like for images, you think that you're going to be more accurate the closer you are to like where you got the actual input sequence? Like say they started you with 20 pixels, so your next pixel might be more accurate, you think? So is there like, for all these numbers, are they giving the same number of pixels for an image or things like that?
It's the global approximation, right? So it's just how, as Hassan was saying, it's just how well you're able to guess in general. It's not talking about some specific image necessarily. Does that make sense? So it doesn't care about whether or not you guessed. Like if you took an average, for example, right? You're not talking about any specific value. You're talking about the whole, the trend. But so it's the same thing.
I think that if you were only predicting 2 pixels out, then you're going to be more accurate than if you're trying to predict 100 pixels out, even if you're averaging them both, right?
It depends. I think we should probably take this offline, but it just to maybe for people at home, it depends, right? Because if you think about it in terms of a sequence, by the 10th pixel, I now have more context information that I can use to inform my next step. So you could actually argue the flip side, that the earlier things would be the most indeterminate because I have no information on which to go by, or I only have the original random seed or whatever with old LSTMs and stuff like that, sometimes or models, they would sometimes just give you like black dots, or like almost all things have a black square in the top left-hand corner, so we'll just do that, and then you go. So it really depends on the assumptions you've made when you built your model, if that makes sense.
So here in table 2, we also see the same time per iteration. So as we can say for CIFAR10, which is images, you can see it will perform better for strided than it will for fixed, as I described earlier. And then for NWIC 8, it will perform better it should perform better for fixed than strided. But here we see, yes, performs better for bits per byte, but for time per iteration, well, not as good. Okay.
So it claims that by proposing this type of sampling method, it has also increased the information gain from the attention rather than getting all the noise as well, because attending to all previous nodes. Is that idea?
Yeah, that would make, yeah.
Because right now the sampling technique says that I brought more information to the system, so I guess I have better performance.
You could almost think of it as being like there's just less noise because I don't have to consider as much stuff.
As much information because it's sparsely done. Okay.
Is it consistently better? Is it consistently better than dense attention?
I mean 0.99.
Yeah, not
I would guess not consistently.
yeah.
Comparably better.
And I've heard other people trying to get. I saw another talk from another gentleman who was trying to improve on this, and it was like 0.1. It's a very, very insignificant benefit.
But remember, we're talking in a completely different normalization space, right?
Okay.
So that 0.1 in some sufficiently large space could be very large. I don't know. And NWIC
it's huge.
Like the context when it's 12,000.
Yeah, it's pretty big.
I think the point here is that you are using significantly less number of parameters.
Yeah.
While achieving slightly
achieving
better
the
results.
same.
For sure, that's
Or better
and it's
results.
faster.
Or
Yes.
comparable at least, right?
Yeah.
Yes.
Even comparable is actually a win. Yeah.
So especially for this one here, it says that we observe increased compression of NWIC 8 with longer context, suggesting the sparse transformer can effectively incorporate long-term dependencies. Even with all that sparseness, we can still have long-term context. So we can give attention to something that, based on context of something very, very long ago, and hold on to it to predict something else in the future.
Really think about it, like I think a really nice way to think about it is fully connected layers versus convolutional layers. We should all be relatively familiar with this idea, right? And so when they showed that you didn't have to have a fully connected layer everywhere, but you could use convolution and only have to consider a small piece of the image at each layer, and then have a fully connected head at either certain segments or only at the end, you automatically have way less parameters, right? So it's very similar kind of idea, but the focus is different now. We're focusing on attention instead. So the structure of how we do that is different.
Okay.
So this, just to emphasize, I think the last table. So basically what it's emphasizing is that you're going far back.
More information is better.
Right.
They're basically justifying why you would ever care to have why you would ever care to have a sparse thing, because going further back in time is better.
Yeah, and it seems to be helping, but to be honest, like until you do
it's so
like kappa stats or some sort of significance testing, I can see there is a trend, right?
Yeah.
There is a trend, so that I guess that helps their argument.
Yeah, it continues to go down from here.
Yeah. Okay. Trying to help.
So this is a performance of a strided sparse transformer on a classical audio data set. So they use mu law encoding at 12 kilohertz as a function of sequence length and the model size. So then they show you here the bits per byte based on a very large sequence length.
What is this mu law encoded?
Mu law is just a type of encoding of an audio sample, an audio wave sample. So they have different type of encoding algorithms to do that.
It's not a record.
Yeah.
Is there like a benchmark they're comparing to here?
That's a good question. I haven't seen any comparisons to different encoding types that will produce a better bits per byte based on the sequence length. But it's still wave audio information, all the same. And whether you use 12 kilohertz, 48 kilohertz, it's just you're dealing with more information. So here they're trying to give you, using mu law encoding at 12 kilohertz, you're trying to get the maximum amount of usable information and make it sound good. Like it's just the minimum, not the maximum.
It's easier actually are you asking about mu law or are you asking about the bottoms?
Well, I guess just because it says it's a classical audio data set, so I was wondering if there was going to be a comparison. It's not a huge issue. Yeah.
Probably that is the data set.
Oh, it's classical music?
Classical music, yeah. So versus jazz or something, yeah. So,
Question.
yes.
How come the sequence length increases and the number of parameters drastically decreases? It doesn't make sense.
As a function of sequence length and model size.
If you're using longer sequence, the number of parameters used should increase, right? This is drastically decreasing.
It's just different setups.
Maybe intentional, yeah.
I think they reduced it to fit in memory or something.
I don't. I got nothing. Yeah, sorry.
So, well, there's a note here. It says, the sample quality, of course, decreases or degrades for greater sequence lengths due to reduced model capacity. So as the sequence length increases and the parameter decreases, of course, it's not going to be as great to predict the next value.
But the thing is, why would you intentionally mix it up? Because then you can't prove anything, right? You either increase your sequence length or you increase your parameter size.
So I think so it says here like the samples clearly demonstrate global coherence over the sample period, but this will be different for different type of play styles. Like you're going to use jazz or rock or classical.
That's not what they're nitpicking on. So what they're complaining about.
Here it says.
What they're complaining about, I suspect, like I feel like I'm going way out on limbs here, guys, but I suspect what they're saying, because you said it's based on, what did you say? Can you read that?
So it's samples are available for sequence lengths of 65K, which correspond around 5 seconds of generated audio at 12 kilohertz. Okay, so then it says they clearly demonstrate global coherence over sample period and exhibit a variety of play styles and tones, softening from rhythmic playing to forceful, based on this input sample.
Hold on.
The constraint they said here is that they want to fit the model into 16 gigabytes. And therefore they had to keep reducing the number of parameters to model the thing that's so long. They were just applying an artificial constraint for some reason, but that's why this happened.
Nice.
There you go.
Okay.
Yes.
That's better than my speculating.
I was going to say effectively that, but I didn't have a concrete thing.
Yeah. So
obviously there's a coupling, right?
Yeah. No,
but it's not that bad, right? Like, sure, you reduce the number of parameters in the model by a factor of 50, and your bits per byte doesn't go crazy.
Right.
And the
which
reason
is actually pretty cool.
Yeah, and the reason why
it's crazy, you know. How do you
I don't know, but what I'm seeing here is an increase of 1, and I don't feel like that. It doesn't feel horrible.
Increase of 1 because everything is log 2, so it's like twice as like 50%.
Okay, but like 50 though.
50% worth. It's not a 50% increase, though. I think is the point.
It's not 50x increase.
5 times
sure,
for 1.
compared to that, yes.
Yeah. So if you're losing you're half as bad or.
But the total size of the model stays the same, which is 16 gigabyte, right?
Pretty much.
So you have only 3 million parameters, but that will consider a longer sequence, right?
Yeah, the constraint is the physical hardware of the GPU. That's why they've kept it at 16.
But I think they can still do just keep the parameter. Probably they can just fix the sequence length over there and decrease the parameters with less and less resources, and doing these benchmarks.
I think, like they say here, the quality will quickly degrade for greater sequence lengths due to reduced model capacity. So I think what they want is to have a greater sequence length to sort of produce more output. That's why they do it that way. Yeah. So if you want to play something based on a small sample, it will play more of that thing based on the larger sequence lengths.
Okay, probably they're just trying to use 3 kind of models to generate the same quality of the samples and doing the comparison.
Yeah, like for the jazz example, you'd have like maybe a small jazz riff as the input, and then based on that small jazz riff, keeping the sequence length longer, we'll be able to play even more of that, but it will vary as it goes along for the produced output. That makes sense, yeah. Okay.
Can I ask a question? Go ahead. When you're reducing the number of parameters, what exactly are you cutting? It's not a number of layers, right? But it's how did you go from 25M to 3M?
I think that is corresponds with different 3 ways of the sparse matrix, no?
So here they say
the size of the hidden dimension.
Yeah, so they have here it's basically the sequence lengths by the factor of 4 requires a reduction in model capacity of approximately 4 square root 4, which is 8. So you're reducing the model capacity by 8 for root 4.
I think you can. The question is, you can do it in multiple ways, right? You can reduce your embedding dimension size. You can differently sample with these factorization methods. But they didn't really specify.
I don't know if I should say that out loud, actually. So I'm not going to say it.
Because basically you want the time. It says here you want you're using factorized self-attention on sequences over 1 million time steps long with the fewest parameters possible. If you don't have enough, I guess, time steps in that sequence, then it's not going to like quantize to give you some produced output. So for the musician, you do quantization, right? So you want to have enough quantization in your input rhythm to be able to produce more of that thing.
Yeah, I guess one last point is, maybe it's made earlier, is you could have kept your sequence length constant and focus on the parameter size, or vice versa, so that we know actually what's happening. Because like I would suspect that the longer sequence length could actually inform the model more than not, and the smaller parameter size would degrade the model, right? So usually what we do this is we keep I'm not sure what the reasoning was as to, okay, let's I mean those 14 gigabytes, they're like you don't have to use all of it, right?
That's right.
You can use but anyhow,
there's 16 gig, for the size of the GPU that you're going to run it on.
I guess we can still speculate what's causing it. Probably a smaller parameter size is causing the degradation, but I mean, I would have loved to see the separate.
I think the trade-off is to take the smaller parameter size in trade for producing a longer sequence based on that sample of the input. And of course, you're going to have degradation in quality, but at least you're going to get something that will generate something unique from that.
Yeah.
Okay. So key takeaways. Mike wrote this one. So one of the interesting findings is that different layer depths have different.
Could you just allow me for one more stupid question? Where does
There's never a stupid question.
Where does that square n in the complexity come from?
The square n in the complexity?
Yeah.
I think we should talk about that offline.
Okay. Offline? Okay.
Sorry, I'm sorry. It's not a stupid question, but
it's not. We can flesh it out some more after. Okay. All right. So we'll do the takeaways. Yeah. All right. So one of the interesting findings is that different layer depths have different types of attention that we saw earlier on with the different images. As you increase the depth, the model goes from more generic, like block around a pixel, to more domain specific, like following the edge of an object. Back in the first section. So here are the 3 discussion points. So the first one is, what is the impact of this architectural information for transfer learning with transformers? For example, it seems natural to exclude layers as they become more domain specific. Anyone want to go with that question?
Actually, I have another question which is somehow relevant to this one. I was like, what is the guarantee that we have these different sampling techniques that they would act on different data sets the same way they did here? For example, you have some type of images and then you are trying to apply to different, for example, there are scenes of buildings and then you're applying to images of people's faces and then having the same like sampling technique would work there, or?
That's a really good question. Like,
so they don't have any mathematical guarantees for that in the paper?
No, it's not in the paper, but it's safe to say that if you wanted to train a model, like have a portion of that trained for a specific type of input vector, then you could do that. I don't see why not.
Remember if we go back to convolution, right? Right here, what we're really talking about are general patterns that you could use to exploit longer dependencies. That's really all it's saying, right? And so there is no guarantee that the type of pattern that they've selected would work in other types of images. However, it is sort of natural to think that, at least in the context of images, that things horizontally proximate and vertically products, like there is information that's encoded on by the axes in an image. But that's just a property of the way we take images, and it's a property of the way our optical system works and stuff like that, right? So that like it's kind of related to why we we don't just arbitrarily slide convolution all over the place, or why we use a box and all like these types of things, right?
Yeah, I think in natural language as well, like the tokens, whether you're going with bytes or you're going with words, are highly correlated. So you remove a few, you'd still be able to see the general picture. And a lot of times you can still, with high accuracy, predict the missing words.
But I do think you're right. If you could inform, but with your domain, the types of filters that you're selecting or the types of sampling that you're selecting, then you should get better, right? And you'll see this in certain domains. They'll be like, we can pick this thing because it works really well.
It'll be interesting to see what they come up with for video with sound in it. Yeah. Because that's gonna have a whole bunch of this. Like you'll have the strided one that'll be doing the sound, and you'll have the fixed one that'll be doing the image. And you'll see what kind of X pattern or check mark. I have no idea.
There's also really
It'll be
weird
cool.
dependencies between sound and vision, or at least the way humans process information.
Yeah.
So
Something came to mind is I remember seeing this site where you can put in text and it will remove all the letters in between the first letter and the last letter. But if you read it, you'll still be able to understand what word it is.
Yeah, that's called holistic reading.
Holistic reading, yeah. So I think
an algorithm like that.
yeah, there you go. So that is something that came to mind of using very little information, but you still have enough context to understand what it means. So as I guess an analogy. Yeah, that came to mind. Okay, number 2. So the authors use row and column factorizations that resemble the intermediary layers of the original transformer. So could we not improve results by preserving the full attention layers at the last layers in the network, which is similar to fully connected layer in standard CNN models?
It's really related to that last thing we were talking about. These are my questions.
Okay, so we'll go on to 3. So this approach resembles a growing trend in deep learning to include stronger architectural priors based on the data domain. So can we speculate on some of the long-term impacts of this trend?
I know that we also just covered
we covered them all.
But again, if people want to, I'm happy to chat about it. But I think we could go to the next.
So I think that's basically it.
No.
So last slide.
Okay.
That's it.
Oh,
yeah.
okay. So then, sure.
So the last one, is this like would you say that's a stronger architectural prior than the CNN?
Well, I guess it depends on how you think about it, because you could say it's a stronger prior to say, let's connect to everything. But I generally would say that if you're giving a much more, if I was like, I know with 100% confidence that if I look at the 7th pixel in every image, I can guess things perfectly. To me, that feels like a stronger prior, right? Like you're saying, you're putting a lot more weight on a very narrow piece of information. And to me, you're doing a similar thing here where you're saying, I know I'm very, very confident that if I just look at the rows and columns, I will get enough information, and I mean, they show that, to actually generate the full image or whatever it is. To me, that feels like a stronger, but I could be wrong.
If I can add to that, one of the things that in reading the other source information for this is to come up with, I think one of the goals of deep learning is to come up with a one general framework that can do everything. You know, you can do text, you can do images, you can do voice, you can do audio, or maybe you can one day do combination of those things. Like, to me, it's like trying to replace the human brain. We can do a lot of great things really, really easily, but
it's worth keeping in mind that different parts of your brain do different things.
Do different things, yeah. And I think it's trying to, I mean, the whole point is to replicate us, right? How we think, how we work.
And especially when you're talking about architecture. So again, I have a cognitive bias here, but because I've looked a lot into this, the underlying neuroscience, and there's heavy duty architectural priors built into the brain. You always will process this information before this information. I don't know, an example would be,
auditory cortex would process things more in sequentially. The visual cortex processes things more.
And there are similarities, right? Like you do have a retinotopic layer in the vision part, so you can see there's actual space roughly corresponds with space. It's weird and deformed, but in the early visual cortex, and there's a tonatonic layer in the auditory cortex, but instead of space now you're doing pitch. So there are similarities in general patterns and whatever, so that's absolutely true. But I think what I'm trying to say is that the fact that things are processed in a very particular way, if we're looking to humans, then we actually should expect stronger and stronger and stronger and stronger architectural priors, not more general. So it's actually the opposite.
The opposite. Okay.
I would argue it's the opposite, but who knows?
Yeah, because I noticed one thing relating to the brain in looking at brain development is something about how as infants it will peak in terms of all of the, I guess, mass and connections, and it starts to become sparse as we grow up till we hit puberty. In other words, it discards what's not useful and only keeps what's there and makes those connections stronger. which is really, really interesting to think we start with so much and we end up with less.
There's also a really nice paper actually that they showed neural networks do a very similar thing as well. When you train even just standard deep nets, they drive, the ideal thing is you drive most of your values towards zero. Again, or regularization does this as well.
It's neuroelasticity, right? You have them, you're very, your
Plasticity?
neuroelasticity.
Neuroelasticity, yeah.
Yeah, so it's like very early on in your developmental stages, you can basically learn anything. That's been correlated with people, with kids learning music better, languages better, better, quote unquote, right? We don't exactly know the entire phenomenon, but as you grow up, it seems to become harder and harder for you to process, for you to learn.
To learn, yeah. I noticed one thing with language, I think it was something Dr. Iwasuki showed, was when you learn a new language beyond puberty, your brain creates a new area for that language. And that's why you always talk with an accent, because it filters through that main part of the brain for your predominant language that you speak. But I think anything with enough practice will allow you to get better at it. Like these little areas develop. So
just want to get us to the math.
The math?
The algorithm per se. So I think one huge implication, which probably is implied in all those discussion points, is that this to me seems as significant as the discovery of CNNs. And here's why. So before the CNNs, a lot of image processing, processing the way we do today was almost impossible. So hardware limitations and all the bottlenecks in the processing. Right now we're in much better position, but back then it was impossible. So right now a similar trends happening with these language models that are sometimes do multitask, like perform on multiple tasks. But we seem to lack, like general researchers or individual researchers seem to lack the computational power to run those experiments. This could, in my opinion, compensate for that. And I think the implication for researchers is huge. You can use much less computational power to almost achieve the same results.
I think that was one of the things I found really, really interesting in researching this, reading on it. It's like, yeah, you can do a whole lot more with a whole lot less. I think of like things that behave like a power law. For example, right? And I think there are a lot of things that we see in nature that distribute itself very, very easily, very quickly, as with a power law. And I think it's something I definitely will continue to watch and follow as it evolves. It's really fascinating.
So to follow on to that, with this type of network, do you get complete translational invariance? Like with CNNs, you have to, max pooling doesn't work that well for translational invariance, but this, it would seem everything is relative to.
I mean, remember, it's translation. You're asking translational invariance of attention, right? So it's a weirder question, I think, than with a standard CNN.
You mean equivariance?
Translation equivariance?
Yes.
What did I say?
Oh yeah, yes. I think that was implied. Yes.
Yes. Sorry, that's what I meant. Yeah. Yeah. But what I'm trying to say is that when you're thinking about what attention does, it's like because.
But attention is always relative to where you are. You're looking a certain distance back. So in that sense, you are completely invariant to translations.
I'd have to think about it more deeply.
I think it depends on the pattern you're looking at, using. I remember the picture where they have the last column as attention vertically. So basically, you cannot translate like horizontally because it's not invariant horizontally anymore. Right? Because you always fix the last column as your attention, as you're looking back with. Okay. Do that make sense?
I guess to make that point, don't we need to you need to have a task that is invariant over translation, and then you need to see objectively if this network architecture can perform it, right? So that's. Sorry.
Yeah. I mean, I think the biggest thing that I always think about when I'm thinking about sequence modeling is that it's what I said before, is that you're always conditioning on the amount of information that you have available to you. So in the beginning of the image, it's different than later in the image, especially if you're using these weird hopping thing, because often by the end of the image, your last few guesses, you literally are going all the way back to your very, very first guess. So in order to really see what translation invariance would mean, you would kind of have to have an image of a certain size, and then you like slide over and see if you start at a different point, whether or not it still infers the entire image the same. As opposed to thinking locally, well, as I slide my window along, I'm getting translation invariance. You almost, like in my mind, I mean, there are ways of constraining, like getting around that, but anyway, yeah, so I think it's a little bit tricky, but hopefully.
What about bias as well? I think we discussed something about bias. There's bias to the input, right? In terms of predicting the output.
Yeah, but I mean, it's more or less the same. But you can flip bias to and use it instead of some of the other words I was using. But yeah, yeah.
Okay.
Florian, you actually did have questions.
Yeah, I had two questions. Like,
yeah.
Given the architecture, they took the GPT model, which was for natural language processing, right? And now they applied it for images and audio. What other domains do you think you can transfer the model to? And how easy or how difficult it would be to transfer the model?
So it's almost like another way of thinking about your question, but from the flip side, right? Instead of saying, are there certain domains where this would not work, you're asking, using the tools that we have available, what other domains would actually work? Or what do we think about that? Somebody said forecasting in my group.
Oh, forecasting, yeah.
So
like weather forecasting?
Economics forecasting. No?
Yeah.
No? Yeah, no. He's like, that's way harder.
Short-term forecasting, maybe.
I don't know.
It
doesn't make it easier. What's that?
Sequence of actions.
Like
behavioral
a maneuver or something like that, or in a video game it does like a certain thing.
Yeah, so potentially then could you maybe apply it to reinforcement learning style models would be interesting.
Yeah.
Not one decision at a time, but like a set of decisions you're going to make.
Yeah.
Given previous decisions already made.
Yeah.
Okay.
I guess it depends on the uncertainty of the phenomena. For example, imagine if you have artistic images, it would be harder to have this type of sampling framework putting on it, because in the artistic, for example, image, you would expect that something irregular happens, right? But when you have realistic images, then applying this type of some sort of general frameworks to the images may, I guess, be a good guess. You know,
it's an interesting thought, yeah.
But like maybe, for example, on the financial things, because we also have a lot of like uncertainty happening. We also have risks which are shown in the patterns of the data, but also like uncertainties which are not reflected in the data. So I guess maybe that's harder to put it. Yeah.
Modern portfolio theory. That would be interesting. Yeah, portfolio design. That would be interesting.
But it's really hard. I think
that would be really hard.
That's
yeah.
why Florian is shaking his head. It's really, really, really hard.
Yeah, that I'm gonna look into.
If you want to use it for portfolio construction, there are like some recent papers on that topic for machine learning. You can check it out. But it's definitely not a trivial problem.
No,
and
it's very hard.
The interesting part is like if you have for portfolio construction, if you take like one instrument, it's like too sparse on the data point. If you take all the instruments, it grows too much complexity. However, if you consider these sparse models, they might be able to be applied to those larger amount of data. But for portfolio construction, like two elements come in together. It's like one dealing with the data, and one is like building the portfolio, where you can apply a reinforcement learning approach to it. You just need to plug in this GPT model into a reinforcement learning. So instead of predicting, you can do it because you just have softmax over your actions, right? If you want to
actually, that's good, interesting idea, because in here you have this, you are having this sequence that you want to predict how you put the attention to, saying, okay, we put a like reinforcement learning agent that tries to find out the best policy of sampling based on the location of in the sequence. That's the idea.
If you look at some of the weird regularization that they use in reinforcement learning as well, when they're smearing out and you're trying to look at more global structure anyway, I would imagine, I'm not an RL guy, so I would imagine that there would be interesting similarities between this kind of technique and some of the weird stuff that I think is weird.
So when you talk about reinforcement learning, the immediate thing that occurs to me is then you need to have a reward sort of function or some sort of cost according with regard to your policy.
But you also
the
have
next thing.
Yeah. I think it's more at the policy level. I think that we're thinking.
Like you can have reinforcement on two levels, right? You try to predict your value, your reward, or you try to predict the policy to guide you to your reward. And then the recent proposed models like the actor critic model, where you predict both. You predict both value and your policy, and then you combine those to make your final action.
Yeah, so I think it was building up to get to here. So then the next step, I'm not sure if I remember my double Q learning deep Q learning pretty well, but isn't it inherently don't you need more runs and iterations by adding an RL cost function?
I don't know.
Because what we have learned in here, like with putting this like prior, the reinforcement learning agent has to learn. So I guess it would be more computationally expensive, but that's my guess.
So one thing you can do is run the same data over and over again. And then other thing is people will generate artificial data, right? You do some kind of random walk simulation of different markets, and then you train on this. Or you do a combination of both, right?
But so yeah, it becomes more expensive with time. But remember, this is a simplification thing, so it would make it more expensive but cheaper.
So what about
It's the opposite thing there, right?
Yeah.
More
expensive
but cheaper.
So it's more expensive because you have to train for longer, but the amount of information you can encode in each step would be
And I
small.
think that's the magic, right?
Yeah.
Which is what you're kind of saying, but it's also what Jeff Dean said in his 2009, his most recent IO thing, right? Was that like the sparsity of these models is very valuable because you can have more models in your toolbox. So therefore, these agents that are using maybe some kind of reinforcement thing to pull the best model now can select from 80 models rather than 10 models. And that will just keep happening and keep getting bigger and bigger and bigger. So transfer learning is like is going to really benefit from this.
Yeah, I think of like you try to identify more problems in the problem space and see, can this now do more with less with that tool and from the solution space?
It'll be interesting to see what this looks like in medicine. Yeah. Especially with the long, when we get a lot more processing power, like you'll have a lot of different models and you'll be able to sew them all together and you'll be able to do the longitudinal view. And it'll be very interesting to see what kind of predictive power this thing has for some kind of symptoms.
Like long-term medical studies, research studies, things like that.
And like we're all getting closer to just feeding everything about ourselves into a little computer.
Pretty much, yeah. Yeah, that'd be quite interesting.
Well, I have two questions. I'm not sure of time.
Check the square root of n.
Okay, then I'll just pick the most important one.
Sure.
Have most of you reached Sutton's bitter lesson and think it's heresy?
I've read it.
Yeah.
I don't know.
So
what's the
Does someone explain that one? Yeah.
the core message was that like computational power is the bigger driver in breakthrough in machine learning.
In contrast to architectural priors.
To manual design.
But this was for reinforcement learning.
That's not in the article. Basically, the bitter lesson is like,
No, in the article he was describing DeepMind and AlphaGo. So he was describing reinforcement learning strategies, and he said that later on, the one with less rules, hard embedded rules, beat the previous models which had more hard embedded rules.
Really?
I don't think he
mentioned
was
in the first
specific
paragraph.
about RL though. I think he was just generally talking about like designing models.
So my counter to that, but I'm nobody, so that doesn't mean anything. But I think the reason why is that constructing reasonable architectural priors is very, 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 very hard. Okay, so most of the time when our best guesses are so bad that if you just throw a ton of computational power at it and let it do whatever it wants, you will actually get a better thing most of the time. I think that's the underlying intuition. And I still think that no matter how you get it, that's going to be true. But it's at what level of abstraction is that true? Remember, I can still do all of this kind of process. I can still have these very big things with very high computational cost at a local level. But if I decide to do my audio processing before my visual processing, that's a prior that, like, I mean, maybe in some universe where you can it can permute every meta system. We can just keep adding hyperparameters indefinitely. But I think at some point it's just nonsense, right? So you have to make some assumptions with whatever architecture you're going to choose, whether that's even just like it has neurons at all or not. Even.
Well, here the simple assumption is just model compression. You compress it, the more the better.
Well, it's not necessarily the more the better, because remember those hyperparameters that they picked, not all possible. So they picked basically how far back are we going to look in the row, and how big a gap is it going to be in terms of the column, right? And they, like the numbers they picked, well, I don't know, I think it was 128 and 256, and then it was something like 16, 32, and 64 or something like that. I don't know. So it's in that range, right? Yeah. But I don't think it's arbitrary, but it's also for the domain.
The model dimensions they arbitrarily chose, I think it was a maximum 1024. Now, I think what you're getting to, what I saw here is basically you have form versus function, and then you have efficiency versus cost. And I think what you're trying to do is maximize your efficiency of computational performance for a given size of the hardware you have, right? So if you look at quantum computers, you either go smaller or you go faster, or you do both smaller and faster. But say, for example, can you go smaller and faster with less information? Then that would be your maximum, to me, maximum computational efficiency. If you can do it at the smallest scale, at the fastest speed, without losing any information, with the least amount of computational power. It's like a triangle.
Yeah,
that's what I think.
Let's leave it at that for tonight. And if anyone wants to sync up with anyone else, feel free to do so afterwards.
Thank you, everyone.
Thanks very much, Mark.